Okay, my test. So sound clear? Please raise your hand. Okay, thank you. All right, so today we're going to discuss chapter 5 and chapter 6 for the Form 4 syllabus, which is I can say that is the most important two chapters in the Form 4 syllabus, because usually SPM there will be located more questions on these two chapter for the uh, questions either in essay or either in the structure question 7 or question 8. Right, so usually they will be more preferring ask the questions on these two chapter. Okay, anyway, for the chapter 5, okay, if you look at the list of formula here, according to last year SPM, so there is only provided two formula, right? Okay, one is speed of wave. Another one is the formula that relates to the interference of wave, okay, which is we use the experiments to determine the wavelength. Basically, that is the concept. Okay, so I think there is one formula is missing here. All right, so I don't think so it's given in the others parts. All right, so yeah, it's missing. Okay, so that formula you have to know, which is actually I can understand why it doesn't provide. Okay, because they want it's just a concept, which is the last time in OSPN there's another formula given, which is F equal to 1 over periods. Right, so these are ones that it should be under these chapters also for the chapter 5 wave, but it's not provided. Then you have to make sure that you know how to calculate frequencies from the periods provided. Okay, so anyway, the main focus on the chapter 5, okay, will be the phenomena of the wave, which is we have the four phenomena here, right? So with 5.3, 5.4, and 5.5, 5.6. There's a four phenomena here. There is a main focus for this chapter. Okay, and the 5.1, 5.2, okay, is understandings for the fundamentals of wave. Okay, which is you need to know. Okay, let us go through. You need to know the different type of wave, right? So you need to know the different type of wave. Okay, and then before that, you must know how the wave is produced. The wave actually produced from the vibrations or the oscillations. Okay, and because of the vibration and the oscillations, either vibration or either oscillations, so because of that, the energy was spread out from that vibrating source. So this wave is the ones that's for the transferring for energy. Okay, transferring energy due to the vibrations or the oscillating system. All right, so this is what we call wave. Okay, because once we have the oscillating system or we have a vibrating system, so there will be energy transfer. Okay, and this energy transfer in the form of wave. All right, so this is how we understand about the wave, and we do have the two different type of wave. All right, so but in your new syllabus, when they discuss the two different types of wave, they will focus on the progressive wave and the stationary wave. This is something different compared to the old syllabus, right? Because in old syllabus, we never introduce about progressive wave and the stationary wave here. Okay, so last time when the student learns, we teach only focus on the type of wave is these two type, which is we have the transverse wave and longitudinal wave. All right. Okay. So transverse wave is and the longitudinal wave is the basics fundamentals how we difference the two different type of wave. Okay, because the directions of the vibrations and the directions of propagation of wave are different. Okay, so when talking about transverse wave, particles vibrate with the directions perpendicular to the directions of the propagations of wave. So these are keywords here about the two different directions. Okay, so which is the directions, wavelet directions, and the propagations of the wave directions. So when they are in perpendicular, so this is a transverse wave. When it's talking about the longitudinal wave, the direction just now, it becomes parallel already, right? So for the longitudinal wave, okay, and these two type of wave, it can become okay. For basically they are the progressive wave. Either is a longitudinal wave or either is transverse wave. Okay, when the moment we have that wave, it will be under the progressive wave. But with a certain term and conditions, progressive wave will become stationary wave. Means that when talking about stationary wave, so that's the means that the wave profile, okay, the wave profile does not propagate with the time. What's mean by the wave profile does not propagate with the time? Okay, so we can make the example for this transverse wave you see here, like this game. Okay, from this game we can see the particle, okay, or the ring, the ring of the spring here. Let's say we look at the rings here. So these ring positions, okay, they have the up and down changing, right? And equilibrium positions, this point is keep propagating forwards. So it means that this point is not fixed all the time. But for the stationary wave, like you see here, stationary wave, the particle at this point, they have a different displacement, which is the displacement we're going up until the maximum, which is we have the amplitude, or they're going down. So the displacement keep changing for the particle when the wave produce vibrate up and down. So the particle positions, okay, is what we vibrate going up and down. But somehow we do have the particle, this one, it always demands the profile, okay, does not depending on the time. So in this kind of wave, we call it stationary wave. If there is a progressive wave, so the progressive wave means that the next moment the wave will be propagating forward. So it means that this point, I say the point A here, there will have the moment for the point A going up and going down when the moment the wave propagating forwards. So this is what we call progressive wave. But if the equilibrium positions always remaining on the same position, it never change up or down, okay, when the wave propagating forwards, this is what we call stationary wave, right? So it's only change the particle displacement up and down on the same position, okay? So, but with the equilibrium position, it never change. So basically, the wave just only remaining up and down on the same positions. Okay. So, but the progressive wave, we keep moving forwards. So this is what we call progressive wave. Okay. And the next one, we also can classify the wave into the mechanical wave and the electromagnetic wave, right? So mechanical wave and electromagnetic wave, the big difference is mechanical wave, we have a medium, requires a medium, and the electromagnetic wave does not require medium, right, to transfer this energy, right? And the rest you can see here. So basically, electromagnetic wave, we are referring to the electromagnetic spectrums, okay, which is they have radio wave, microwave, okay, infrared, visible light, UV, X-ray, gamma ray. Okay, so all these are under the electromagnetic wave, and then the others than that, okay, all actually under the mechanical wave. I included the water wave, sound wave. Okay, so you have to know what's the difference between the first type, okay, from progressive wave and the stationary wave. Second ones, you have to understand what's meant by the transverse wave and longitudinal wave. And then the third one, you have to understand what's meant by the mechanical wave and electromagnetic wave. These three different categories, it's just the way of the difference, how's the way we differentiate or classify the wave, that understanding about the wave. It's just like when we learn about in the chapter 1, when we learn about the physical quantities. So from the beginnings, we classify physical quantity into the base quantity and derived quantity. And if we do want to classify in that way, we also can try to differentiate the physical quantity in the type of scalar quantity and the vector quantity. So it's still differing to the same group. Like this one also referring to the same group of wave. Either you want to understand it as a progressive wave or stationary wave. If you don't want, then we try to understand this group of wave as a transverse wave and longitudinal wave. If you don't like it, then you can change it to classify it as a mechanical wave and electromagnetic wave. It depends on the use, right? And then understanding the properties of the wave itself. Okay, for the transverse wave and the longitudinal wave, we need to know the example, all right? So please remember as a question that I designed for the trial today. So please remember, the only example that we put under the longitudinal wave is the sound wave. Other than that, okay, all is a transverse wave, okay, which is there includes the light wave, water wave, okay, and also the electromagnetic wave. So all these are under the transverse wave, and only the sound wave is the longitudinal wave, okay. But when we look at the wave as a mechanical or electromagnetic wave, then will be different story. Sound wave, water wave, they are under the mechanical wave, but the light wave is an electromagnetic wave. So hopefully that you able to differentiate all this. That is a fundamental about the understanding about the wave. Then the next one, you need to know all these terms, okay, and then their definitions, right? So example, what's mean by the amplitude, okay, what's mean by the periods, frequency, wavelength, and the wave speed, okay. Remember, right? So later on, I will tell you there's some problem in the textbook, right? Remember the V, when we study about wave, we're talking about is a wave speed. We are not talking about the wave velocity, right? We're talking about wave speed. So why we don't use the term velocity? We preferring use the term speed. Okay, because when we mention about the velocity, so it can be includes magnitude and directions. So once you mention the change in the wave velocity, change in velocity means that it can be either magnitude change or it can be either direction change. Okay, but when you mention the change in wave speed, so means there is a magnitude change. So when we study about the phenomena of wave, it's very important that for us to clarify whether the speed become faster or slower, or there is a change in directions. So if we mention the wave velocity change, so we don't know whether the change is because of direction change or actually because of the magnitude change. The wave become faster or slower. Or maybe there's a wave is still same speed, but the direction change, we still mention velocity change. So that's why we preferring only mentions the wave speed. We don't mention velocity. And after that, we will explain what happens to the directions. Okay, to complete the whole picture understanding about the wave phenomena. Okay, and regarding the definitions, usually the SPM question they like focus on the periods and frequencies. I don't know why. Because the student keep confusing about these two. Period talking about time. Time what? Time taken for one complete oscillations, right? How long the time needs to complete one oscillations or the one complete wave. Then the frequency talking about the quantity. Okay, the quantity. How many numbers of complete wave or complete oscillation can be made in 1 second. So that's why how we calculate the frequency with the periods that we have with the formula F equal to 1 over T. But this not provided in the list of formula. Okay, so I think that when you need to count, you make sure that you know lah. Okay. So one more things that you have to understand the meanings of the in phase. Okay, the meanings of in phase. So here textbook given the example we're talking about the in phase. because we're going to use it to explain the meanings of the wavelength. All right. So I just highlight this one for you. Okay. And also for the longitudinal wave, there is a way how we understand the meanings of in phase to point out the length or the gaps to show the wavelength. Still remember, I told you when you ask to label the wavelength, make sure you show the borderline. Okay. So in this case, you see for the longitudinal wave between the different regions here, compressions region and the diffraction region. So when we want to point out the wavelength, so make sure you take the center of the region. All right. So just same as the figure 5.14 given in the textbook. And also for the transverse wave, okay. So when you point the one wavelength, okay, label the one wavelength in the like game. So make sure you show the borderline, okay, from way to way as your reference to have a one wavelength. Okay. So regarding the wave speed, how we get it equal to the V to the F lambda. So all this is already explained here. So I don't want to go through again. So okay, and you have to know how to do the calculation when you provided the wave motion in graph. So we have the two different kind of graph. So which is a displacement against time graph and the displacement against distance graph. So when you study the graph, make sure that you alert what is the graph axis provided the informations. Okay, especially it's about the x-axis. X-axis, make sure you get to know what is the quantity presented for the x-axis. When it presented is a time, so means that in the graph you only get to know about the periods. From the period you can calculate frequency, but you can't get any information about wavelength. So there is no wavelength can be get. All right. So or you only can get to know about the amplitude to the y-axis, and only you can get to know about the period and do the calculation to find the frequency. But when the graph provided is a displacement against distance graph, so you can get the information about the distance, means that you can get the wavelength, but you can't get periods. You cannot calculate frequency from the graph. So you have to base on the additional information provided. Right. So please do not confuse. Okay, and please alert the labels of the axis given. All right. Okay. Okay, all this done. Okay. So the next one, the damping and resonance. Damping and resonance, right? So they are related, but totally different concept, right? So when the wave, okay, how to say, when for the any oscillating system, in ideal conditions, by theoretical in ideal condition, when there's no loss of energy, so the oscillating system will vibrate freely, right, or oscillate freely, right, without any actions of the external force. Then for that moment, it have a frequency. The frequencies we call it natural frequency, right? Natural frequency, right? And then this natural frequency it won't change. It won't change for the any oscillating system, right? So let's say example, when I give you a length here, a length of the pendulum, right? When you oscillate, compared to the other one with the longest length, right? When you oscillate. So with the different length, you have the different natural frequency. You have natural frequency. Okay. And but in practically, so these natural frequencies of the different length, it unable to cause a system have a maximum amplitude, right? So because when it start oscillate, there will be energy loss to the surrounding, and this energy loss we call it damping, right? So somehow the frequency is different between the different length because they have a different natural frequency. Only the moment we let it oscillate, okay, we unable to get the maximum amplitude because the energy is already lost to the surrounding, or energy lost due to the internal damping as well. Okay, so therefore, when we supply the external energy towards the system, right? Once the resonance occurs, then this system will be said to oscillate at its natural frequency, and the time you will get the maximum amplitude for the system. All right, so that is how we understand about the damping and resonance. Okay, so when the damping occurs, okay, due to the loss of energy, either because of the internal factors or external factors, right? Somehow it wasn't affects the periods, right? That's why I mentioned just now, when you let it oscillate, so different length have a different natural frequency, okay, due to its length itself, okay, in the example that I gave you, right? So once the energy loss, so then the oscillating system will have a smaller and smaller amplitude, okay, decreases, okay, over the time, but the time taken to complete oscillation is still the same, only decrease is the amplitude. That's why when we look at the graph showing the damping oscillations or the damping wave, so you can see that the time taken, right, for one complete oscillations is all the way same, right? They have the same constant periods. They have the constant periods. Only the difference is the amplitude, and amplitude will be gradually decreases. Gradually decreases means if you look at the amplitude against time here, so it's a curved line. That's why we call it gradually decreases for the amplitude. All right. Okay. And here is the two different type of the damping here. So, and also includes why the energy loss. If the external damping, the energy loss due to overcome the frictions of the air resistance. Internal damping, say, because of the stretching and compressions of the vibrating particle in the system itself. All right. Okay, so this is a damping. So then the resonance, okay, okay. So if the periodic force applied to the oscillating system at its natural frequency, then the oscillating system say to be resonance at resonance. So during resonance, system oscillates at its natural frequency, okay, and it will have the maximum amplitude. Okay, so here's the example for the, okay, to study about the resonance effects on the buttons pendulums here. So when we use the X as a driven frequency, so when we start oscillate the X pendulum bulbs here, so the energy will transfer through the string. So others pendulum A, B, C, D will be start oscillate as well because it's receiving the energy from the X. But after some time, you only see that only the C will be oscillate at the maximum amplitude compared to A, B, and D. A, B, and D will have a smaller amplitude. Only the C will have the same biggest amplitude with the X because they are the same length, so they will be oscillate at the same natural frequency. So the C will able to resonance occurs on the C, so they have the maximum amplitude, largest amplitudes compared to the others. Okay, and then the effects on resonance in our daily life, you have the either is a constructive effect or the destructive effect. So for the destructive effects, so here's also some example. Given destructive effect, okay, it will be cause the bridge to be collapsed. Okay, it happened in the history. All right, so you can go through it. And constructive resonance. Okay, example, we can use it into the tunings of the musical instruments. Just like the mechanic come to your house, okay, to tune the piano. So it's also based on the concept of the resonance, right? Okay, and then you also use a microwave oven that can heat up the food. Okay, that one also based on the resonance effects, right? And then the receiving the channels, either the TVs or either radio, is also the constructive resonance effect, right? So here are the fundamentals understanding about the wave. So far, okay or not? Okay. So can I proceed to the wave phenomena? Or do you have any questions? If you don't have, proceed to the next phenomena. So please raise up your hand. All right. So I'm going to make the conclusions, all the phenomena together to highlight what is the importance part that you need to know. You have to know. All right. Okay. So for all these four phenomena, okay, when we put it together to compare, now you look at here. So first, we're talking about the frequency. Frequency. So this one, unchanged, 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 unchanged. All right. Okay. Then the wavelength. Okay, wavelength, unchanged. This one, yes, it's changed. Okay. And this one, unchanged, unchanged. Okay. So the next one, the wave speed, right? Wave speed. So this one unchanged. Okay. This one, yes, it's changed. And this one unchanged, unchanged. Okay. So and here amplitude, amplitude unchanged, unchanged. And this one, yes, it's changed amplitude. Okay. And this, yes, it's change amplitude. Okay, change amplitude. And the directions. So this one, yes, it changes directions. This one, yes, it changes directions. Then this one, yes, it changes directions. So this one, no, it's not in change directions. Okay, and energy. Okay, what question is it? On okay, is the questions here? Okay, I haven't shared the screen. I thought I shared the screen already. Finally, got someone tell me. I thought I shared the screen just now. Do so can see the screen now? Wait. Oh, because just now I closed this one. Oh, I thought it's a different Chrome ID open. Sorry. Because just now I closed it. So, but beginning when I explained about the graph and so on, you can see the screen or not? Or you just only listen? Oh, beginning can, but just now listening, I close it lah. Oh, okay. So now look at this one. Okay. Sorry, technical problem. All right, okay. So the energy, energy here, not change. Okay, it doesn't make any change of energy. This one, yes. And this one, yes. Okay, so regarding the energy here, because all the wave phenomena here, we are discussing under the ideal conditions, theoretical ideal condition. Practically, you have to know, practically, no matter what phenomena we observe, practically, we will still have a change of energy because of the damping of the wave, all right? But when we discuss about the phenomena, so we discuss based on the ideal condition. So based on ideal conditions regarding the phenomena itself, whether it will make the energy change or not, okay? So this energy is talking about how it make it change. It doesn't mean that it increase or decrease. We just want to, because based on the conservation of energy, okay, principle conservation of energy, we cannot create energy, right? We cannot destroy the energy. The change of energy here is just want to know how the energy per unit area per unit area is different based on the phenomena. All right, so this is something that I want to highlight here. Okay, so the diffractions of wave, which is the third phenomena here, the third phenomena. So because when the wave round the corner or pass through the obstacle, it will spread out to a larger area. So that's why the energy will become smaller per unit per unit point or per unit area, right? Because it's going to cover the bigger area when they have obviously diffracted. Therefore, the energy per unit area is become smaller. But overall, the energy is still the same. All right, overall the energy is still the same. Only the same energy will cover the bigger area, so that's why it makes it smaller per unit point. Okay, and then the indifference of wave also, when we have the superpositions for the two coherent sources. So because when the moment they're overlapping, so it will become constructive interference. When constructive interference, you have the biggest amplitude. All right. So when you have a bigger amplitude, therefore you are combining the two wave energy. So we're increasing the amplitude. Therefore, you have the highest energy on the point. Okay. So when the constructive interference, if the destructive interference, you are destroying. Not destroy that. Means that when the moment the superpositions of the two coherent source, it will cause a resultant displacement become zero. Then for at the moment, it's just like become no vibrations at all because there's no displacement. So it seems like the wave is lost. Then that one can consider as energy becomes zero, right? Okay, so because of the reduced energy in that destructive interference, therefore it will cause the energy increase in the constructive interference. Right, you may understand that way, but somehow about the energy is not the main focus when we study about the properties of the phenomena of the wave. Okay, because we are more likely focused on the amplitude, lambda, and the wave speed. Right. Okay, so remember, no matter how all these wave phenomena we are studying on the wave is already produced from the vibrating source, okay, or the oscillating source. That's why the frequency it won't change, right? Frequency it won't change. So no matter what phenomena, okay. So then when you put it together like this, you can see, and only the second phenomena, only second phenomena, it will cause a change in lambda, change in wavelength, right? So because this change in wavelength because of the change in the wave speed. The wave speed causes the change of wavelength. Okay, remember we have the V equal to F lambda. So when the F is unchanged, remain constant, therefore V over lambda also remain constant. So then we have the V1 over lambda 1 must equal to the V2 over lambda 2. This is the one that we apply in the diffractions of wave for the second phenomena here. So when the speed change, right, then it will make the lambda change. Okay, so this is one of the formula, okay, that will be involved in the calculation, but also it's not provided. It's not provided in this formula here because it's based on the concept f from here. It's based on the concept when the f is constant. So we did arrange the formula. So we make f equal to the v over lambda. So equal to the v1 over lambda 1 equal to the v2 over lambda 2, so that it will lead to the same frequency. This is what we apply the calculations for the diffractions of wave. If you look back to the previous questions, so here, this is the one in the question 14, okay, for the last year SPM. So what is the variables that cause a wavelength decrease? Right? What's the variable that cause a wavelength decrease? Right. So here, volume definitely is wrong. Nothing to do with the volume. Right? Frequency is constant. Frequency constant, it doesn't make the wavelength change. Right? So frequency constant, so that's why it doesn't make the wavelength change. The depth, yes. Density, no. Why the depth will cause a wavelength change? Because when the left change, it will make the change in the wave speed. When it make the change in wave speed, so that's why you make the change in wavelength. That's why the depth is the one to cause a wavelength decrease. So as you can see here, we have the deeper, we have the bigger d, bigger depth. Here we have the smaller d. Okay, so okay, so this one we have the biggest d, and this one we have the smaller d. All right, so this is about the concept. Okay, and okay, so last year, paper 1, they asked about the bottom paradigms here. So based on observation, which the following statement is correct? So like this one, okay, J oscillate faster because it has a shorter length of the pendulum string. All right, so we have the shorter length, so it will have oscillate faster. What's mean by the oscillate faster? Okay, oscillate faster, is it means they have shorter periods? Okay, so if yes, so you can carry first. This one seems like correct. Then we go to the next one. Pendulum K. Okay, pendulum K is here. Okay, with the maximum amplitude because the natural frequency is same with the pendulum X. So K and the X same length, so have the maximum amplitude. This is correct. So maximum amplitude because there's a natural frequency same with the pendulum X. This one is correct. Okay, and pendulum L oscillate faster because it's absorb the energy created by the pendulum J, K, and M. Okay, so this one totally wrong, right? Because the energy is transferring from the X. So it's not because of the J, K, or M. Pendulum M oscillate with the maximum amplitude because the energy absorbed, okay, absorb is maximum, so it's wrong. Okay, so now the problem is the A. Pendulum J oscillate faster because you have the shorter length of the pendulum string. So what is your answer? Which one will be correct statement? Which answer you prefer, A or B? A or B? If you look at the answer, I don't believe the answer will provided is a B lah. Because follow a concept, the answer should be the B. Where is the answer? Okay, on answer. Question what? Questions 13. Right? So as I mentioned, question 13, it will give answers B. All right. Okay. But if you if the X oscillates already with J with the shorter length, so actually it will be oscillate faster. oscillate faster, only that it doesn't have the biggest amplitude. And then the frequency, okay, why is oscillate faster? Because the shorter length, the natural frequency is natural frequency will be higher with the shorter periods. Okay, with the shorter periods. Okay, then for actually it will be we can say that it oscillates faster because it's a shorter period. But somehow this meanings of the oscillate faster, because the term here, oscillate faster. Faster means that example, okay, we're talking about the same length system. Okay, with the bigger amplitude. When we let go the same pendulum from the different height, which is this position A, position B. If you let go the pendulum from position B, it will be faster, oscillate faster. But the period is still the same compared to the we let go the pendulum from the positions A. Positions A let go because of the smaller amplitude, it have the smaller energy, therefore it will be oscillate slower. But the periods were still the same. That's why the understanding about the oscillate faster, okay, usually when we give the explanation, we don't mention this term because this term is too general, right? It doesn't show the concept whether the periods is different or not, okay, or the frequency difference or not, right? Okay, so I don't really prefer you learn give the explanation with the this term oscillate faster or slower. Okay, try to avoid it. Just focus on the using the physical quantity in your explanation is will be better. Right, so that's why after compare, so for node lot, okay, so we're going to choose answer B lah. Okay, so then the next one, okay, so this is about these diffractions of wave. Okay, and the first phenomena, it wasn't make any change other than the change in directions and the change in directions. So this part you have to understand based on the incident angle and the diffracted angle, just like the way I understand about the mirror. All right, so it's only change in directions, so it doesn't make change in others. Okay, and then the second phenomena, the direction definitely will change. Okay, so but it still depends on the angle. So only the second phenomena you have to alert. You have to alert about the way we study on the water wave, light wave, and the sound wave. Because of the diffractions of the wave here, right, this second phenomena, you have to alert about, okay, the difference in the light wave, sound wave, and the water wave. Okay, because we need to know how's the wave speed change in this different type of wave, right? So the light wave, the wave speed change due to the different optical density, right? Due to different optical density. So when the light travel in the optically denser, okay, optically denser, it will have a slower speed, lower speed. Therefore, it will cause the wavelength become shorter. Okay, and vice versa for the optically less than medium. So please take note for this. And then the sound wave, how the wave speed will change for the sound wave. Okay, it have the three different situations. First one, the sound wave will change because of the different density of medium. We're talking about density of medium. We are comparing about the solid, liquid, and the gas, a different state of matter. Right. In solid, sound wave will travel faster. Okay, because sound wave is the ones need medium to transfer the energy to the vibrations of the medium. So when the solid, so the particle will be stick closer, then for the vibration will transfer faster through the particle by particle. So because linked tightly, so that's why sound will travel faster to the solids. Okay, but in the other ones, if we comparing the sound speed, right, traveling with a different density of gas, different story. So when we have the denser gas, actually sound travels slower when we have the denser gas, because denser gas the molecular mass of the gas particle is bigger or higher than the lower density gas. Right. Due to the bigger molecular mass, then for the particle, the particle itself have the higher inertia. So when the sound energy need to transfer to the vibrations of the particle, then for due to the higher inertia, it will take time to overcome the inertia. Then only the energy can be transferred to the vibrations. So because of that, denser gas, it will cause the sound travel slower. So these two concepts is really important. If you don't understand, then it will be conflict. Because denser medium sound travel faster, but the denser gas sound travel slower due to the different reason. Okay. And the next one is about the temperature of gas. When the higher temperature A layer, it will cause the sound travel faster because higher temperature, the particle have higher kinetic energy. Therefore, the vibrations of the particle will be transferred faster because of the high kinetic energy for the high temperature, right? And there will be the phenomena discussed in the textbook about this different during daytime, during nighttime, the sound travel faster and slower and so on. So once the speed change, it will affect the wavelength. So make sure that you understand about this. And then the water wave. Okay, water wave, how's the speed change? The question we already discussed just now. Okay, it depends on the depth of water. So when in the deeper water, okay, in the deeper waters, the speed will be higher. Therefore, you have a longer wavelength. Okay, so after that, based on the change in speed, right, slower, faster, then you should know whether it will deflected towards normal or deflected away normal. Okay, all this it will make the diagram change lah. So make sure that you learn how to complete the diagram. Either it's for the water wave or either it's a light wave, and sometimes it will also about sound wave. Okay, so all this is already given in the textbook. I just highlight the importance part. Okay, so make sure all the drawing diagram for this one example, okay, like this. So how we complete the diagram like this one, showing the textbook about the first phenomena deflect, just like the deflecting of mirror. I'll focus on the directions, right? Focus on the directions. Okay. Then after that, when you complete, make sure you see the wavelength is remaining unchanged, right? So you go through again about this part. If you have a problem, please text me, right, or text in the group. Then I can show you further. Okay, and diffractions of wave, second phenomena. So you also need to learn how we complete the diagram. All right. So when in the shallow region compared to the deep region, so shallow regions, the speed will be slower. Okay, so when slower, it will bend towards normal with a smaller angle, so with a smaller wavelength. In this case, second phenomena for the water wave. Okay, I like to remind you regarding the 4S concept. As I mentioned before, this 4S concept. So shallow regions, first S, shallow regions, slower. Second S, slower, smaller anchor. Okay, smaller anchor and shorter lambda. So 4S concept. All right, so make sure that you remember that. Okay, and right, so 4S concept, shallow region, slower, smaller anchor, shorter wavelength. So this is applied here. Okay, smaller anchor, compare this one bigger anchor, this one smaller anchor, shorter wavelength, okay, slower, so on. So this table also you can see when to the shallow region, smaller anchor, decreasing wavelength, okay, decreasing speed, 4S. All right. And make sure you learn how to draw, complete the diagrams lah. Okay. And this is the one about the sound wave during the daytime and nighttime due to the temperature affect the speed of sound. So these are another ones, okay, for the water wave, diffractions of wave. So, and then here's the calculations. As I mentioned, this formula is not provided. Okay, because it's a concept, then they'll only give you the general equations. So you're going to learn how we apply it. Okay, when you solve this problem, please be alert. As an example for this paper ones, you see, if ask a question, it may give you a length here, and then it give you a length here. So do not simply straight away take this length LA, LB as a wavelength to do your calculations. Please make sure that you understand the concept. We are looking for the wavelength. We are not looking for the length across a field wavelength. So like this one example here, make sure that you study how many wavelength across with the range provided here. Okay, from here you can see this one from the throat toward the throat here. How many wavelength? We have the 1 wavelength, 2 wavelength, 3 wavelength. So the LA by this ligand label, it consists of the 3 wavelength. And the LB here, we have the 1, 2, 3, 4. We have the 4. So LB consists of the 4 wavelength. Okay, so wavelength 1, wavelength 2. So make sure that you have to substitute is the wavelength, is not the length across a few wavelength. Right. So I think this one is example calculation is already provided in the textbook lah. So based on the example 2 here. So this one. Okay, so then the third phenomena, as I mentioned just now, third phenomena, so that all remaining unchanged. Okay, there's no change in the lambda, there's no change in the wave speed, only change is the amplitude and the directions. So especially about the energy, we will be specific discuss energy on the diffractions of the wave for the third phenomena. Right. So and then for definitely will make the change in patterns lah, in the patterns. Okay, so the concept here is whether it will be obviously deflected or not, it depends on these openings. This distant opening. All right, this opening, we're going to compare with the wavelength. So if the openings, is the opening okay less or equal to the wavelength, therefore it will be obviously diffracted. It will be obviously diffracted means it will make the change in bigger directions. Okay, but if that opening is bigger than wavelength, then it doesn't make obviously diffracted. Right. So here is given already. So it's mentioned here, there's no change in wavelength, no change in the frequency, no change in the speed. Amplitude, yes. Amplitude decrease because of what? Because the wave energy is diverged and spread out to the wider region. So that's why the energy will be divided by the bigger area. So per unit area become less, therefore we have a smaller amplitude. And the directions of the propagations, so from one direction to many directions. So that's why I give a conclusion here, direction is changed on the diffractions of wave. All right. So here you are, and you can see that it's bigger, make the bigger change. All right. So here is the example. Again, you're going to learn how to compare it. So this one, you see this opening D compared to the lambda here. So the D is much bigger than the lambda. Therefore, it will be slightly diffracted. When slightly diffracted, there's no make any bigger change. So after diffracted, so it was slightly changed in direction on the edge here. So basically, it was still remaining same. It's still remaining same. And when you draw, make sure that you understand there's no make any change in the wavelength. Right? Okay, but here you see that this D compared to the wavelength, so the D almost same as wavelength, so therefore it will be obviously diffracted, it will spread out to the large area. So that's why it will be make the change in pattern. Okay, only the circular wave, it will make it bigger change to the wider. Okay. So then here is the same lah. We have the same D, but this same D compared to the wavelength, so it will make the result of the diffractions. Okay, for the shorter wavelength, because shorter wavelength, then the D it look like bigger. So then for this one, for the shorter wavelength, it will have a slightly diffracted. But longer wavelength, make the D become smaller. Then for longer wavelength, it will be easily diffracted. This is also why the radio wave compared to the others wave, example, the microwave. Radio wave is the wave have the longest wavelength in the electromagnetic spectrum. Then for the radio wave easily spread out when passed to the any openings or around any obstacle, because radio wave have the longest wavelength. So that's why when you want to receive the radio channel, as long as you got the antenna, so you no need to fix it into the specific directions. Okay, you just make sure the antenna is connected. Therefore, you can easily receive the radio channel in everywhere you are. All right. Okay. But for microwave, infrared cannot. Microwave, infrared, you have to focus on the specific direction because it's not that easily diffracted. Right. Example, the remote control. For the TV, remote control for TV is using the infrared. So you have to point the remote control towards the TV. They only can change. You can only change the channel, you can control it. And compared to the radio remote control toys car, so you can see that they're holding the controller, and then no need to point directly towards the car. The car can easily control even the car behind the person, right? Because it's using the radio wave. So here is a concept that we apply for the diffractions of wave. All right. Okay, so and the last one, interference of wave. Interference of wave, okay, you have to understand the meanings of the principle of superposition. Principle of superposition is the ones to explain what happened when the two waves overlap, why it will cause it have the resultant displacement. Okay, so we explain it under principle of superpositions. Okay, because once the wave is overlapping, so resultant displacement equal to the sum of the individual displacement of the two waves. So when the moment is A plus negative A, so the resultant displacement becomes 0. And this, okay, we explain it based on the principle of superposition. When the moment we have the negative A plus negative A, when the wave overlapping, so we have the negative 2A. So this is also under the principle of superposition. Only the result of the different resultant displacement, then we call it, we have the two different type of the interference. Because interference of wave is the ones that superposition of two or more coherent sources. So make sure that you're able to know what's meant by the coherent sources lah. Okay, so when the moments that we have the constructive interference means that it's the moment during the superposition we have the bigger resultant displacement, or we have the bigger amplitude. All right, this one we call it constructive interference. If the moments that during the superpositions we have the zero resultant amplitude or the zero resultant displacement, we call it destructive interference. All right. Okay, so interference occurs by the water wave, light wave, and the sound wave. So you have to understand the way how we study the result. Okay, for the water wave, because the water wave is visible, we can see the wavelength, we can see the amplitude. Okay, we can see there's a change in amplitude and so on. So that's why in the water wave we have the name on the result of the interference of wave. So we have the name that we call this one. We call it antinode point. We call the node point. So and then we have the point linked by the antinode point is called antinodal line, and the nodal line. So the way how we study about the x. Okay, so the distance x and the distance a and the distance d. So all this you must know, because all this when we combine, we have the one formula, okay, to let us calculate the wavelength with the lambda equal to x over d. All right. So okay, but for the light wave, okay, light wave, we have to understand the concept, because this formula lambda equal to x over d. So the question will ask you about the relationship. They ask you the relationship between the a1 x1 equal to the a2 x2, or you can ask you the relationship a1 over d1 equal to the a2 over d2, or you can ask you the relationship x1 over d1 equal to x2 over d2. Okay, so all these actually just only rearrange the formula So example, A1 X1 equal to A2 X2 is the moment that we make lambda D equal to constant. Right? So when lambda D equal to constant, so A1 X1 may equal A2 X2 lah. All right. So what we can study on that? So it means that when you have the different D, so like this one, here there is your D1, here there is your D2. So based on the D1, this is my X1, and based on the D2, this is my X2. So from here you can see D and X is directly proportional, right? So if the lambda and the A is constant, but if we study on the other way, let's say lambda and the D is a constant, then what we can study on the different A. So you have to draw the ligands lah. Okay, you have to draw the ligand to see the different A, how it affect the X. But right from the formula, you know that it should be inversely proportional because A1 X1 equal to A2 X2. Right. So you have to draw the ligand and then only compare. Right. So this is a question that SPM like to ask lah. Okay. So please study on this. And then when we're talking about the line wave, so it may give you questions. What happened to the result if a red color laser light change to the blue color laser light? So you have to understand the red color and blue color because they have a different wavelength. So the wavelength itself, it will affect the result either on the A, either on the D, either on the X. Depends on what the question asks. So always only study one quantity affect the other one quantity. Then the rest will remain as a constant. So we're not going to study how the one quantity affect the other two quantities. Remember, we always study one manipulators, one responding. So that's why you always see that the relationship between two quantities. We never see the relationship between three or more quantities. Okay, we only see one, how to affect the other one. And then the rest will be remaining as a constant. So this is how we apply this formula. Okay, and then one more thing, other than these four quantities here, another one you must be alert about the frequency. Because when the speed constant, so the frequency will affect wavelength. Based on the formula, V equal to F lambda. So when the speed doesn't make any change, therefore when we change the frequency for the source, and the frequency will affect the wavelength. Once the frequency affects the wavelength will affect the result either on the A, either on the X, either on the D, depends on what question want you to study. Okay, and then this one usually will be on the sound interference of sound wave. And I already discussed before with the one past year SPM in the old syllabus. Okay, so different because the sound can easily generate by the different frequency from the generator. Therefore, it will affect the wavelength due to the same speed. Okay, so this is something you have to alert. Okay, for the another one, interference of light wave, we were preferring using the smaller A. Okay, on the young number 3 experiments, right? Smaller A because it will amplify the X. With the smaller A, X will be bigger. So when the X bigger, then easily for us to measure. Okay, why we need to amplify the X to easily measure? Because wavelength of the light wave is very, very, very short. So when we have a very short wavelength, the result on the X will be very short. So to make sure that it can easily to be measured practically, so we need to have a smaller A to amplify the X. Okay, but somehow the X is still very small, so that's why when the interference of light wave, we will measure across a series of X, just like the way we study about ticker tape lah. So when across a series of X, so you have measure the length, you have to make sure this length is consists of how many X, then you have to divide it to find the X, then only can substitute into the formula. All right, so please alert about this lah. Okay, but for the sound wave, different story. Sound wave, because the wavelength is longer, so when doing the experiments or practically when we apply the interference of sound wave, we always split apart the two speaker. Because when we split apart the two speaker means that we have the longer A. Longer A, it will cause the X become smaller. X becomes smaller is an advantage to produce a better sound effect because When the X smaller, it means that the dotted sound and the dotted sound, they will cover the soft sound region, so that we don't have the obviously soft sound region for the person stand there will be always heard the soft sound. Okay, if the X smaller, then for the loud sound, they will closer, so it will help to cover the soft sound region to make the overall have the good quality of sound effect. Okay, but if you smaller the A, when you put the two speaker together, smaller the A, so it will be amplified the X, bigger the X. On bigger the X, so it means the loud sound, soft sound, loud sound, soft sound, it will split apart further distant. Therefore, the person stand at the middle of the soft sound region, is unable to hear the dark sound. So means that the person next to him split apart, always heard the loud sound, but if you are the one stand on the soft sound area, so you're the one always don't know what the person talking about. Just like maybe happen like the day during your ujian lengah, right? So I don't know. Okay, so this is about the independence of the wave. Okay, and here's some example applications. And the electromagnetic wave, so as I mentioned just now, you need to know, here you need to know all the electromagnetic spectrum in their order, how we arrange it according to the increasing frequency or either in the increasing of wavelength and so on. So you must know the order. So just like showing this figure 5.7 from the radio wave until gamma ray. So either in the way of the increasing frequency or increasing wavelength, and vice versa. Okay, so the applications, you no need to exactly memorize all lah. You just need to get to know lah, right? So sometimes the student were confusing about this, what I mentioned before this about the telecommunications lah. Okay, communication. So the student confusing. So microwave, they were both using the communication. So how to differentiate it? Okay, so remember for the microwave we use in the telecommunications, right? It will involve what? It will involve the satellite. Okay, when you use a microwave, it will use of the satellite. But the radio wave, we no need use the satellite. We only need the station to station. Okay, so one of the questions maybe will ask you, for example, when you want to receive the channel, for example, the HFM. So HFM, you want to listen to our YB Kaidi become the DJ. So you're traveling from Johor to Selangor. When you come to the different stage, you have to switch the channel setting to receive the same channel. Why we have to do so? Why we don't put on the same frequency? Why we need to change the FM, right? So if the station to station they have the same frequency, right? Then the interference will occur. When the interference occurs, so the certain region will be on the dead zone, because the certain station or certain area, housing area will be located at the destructive interference. Therefore, they will receive nothing. Right, so there's a reason why from the station to station on the same channel they have to change different frequency. Okay, so they avoid the destructive interference occurred. Okay, but this one is not specific mentioned in the textbook, but it's one of the applications for the interference of the radio wave. Okay, that's all our chapter 5. Okay. Is there any questions? Okay or not, chapter 5? Do you have any specific question you want to ask? If not, maybe we proceed to the chapter 6. Chapter 6, I will go a bit fast because that day I already discussed a few times in the schools already. So later I will go through some importance only. Okay, is this okay? Chapter 5 is okay? Please raise your hand. All right. So as I mentioned, you see the chapter 5, I take 1 hour plus, you see. Okay, because there are a lot of content, okay, considered in the chapter. Same also for chapter 6. This is also the reason why SPM there will be more focus on these 2 chapters, because of the knowledge content inside is just too many compared to the other chapter. Okay, there are too many things can be asked. All right. All right. So the next one, chapter 6, here, light and optics. Okay. Give me 1 minute. I go and drink water first. All right. Okay. So here, okay, some example question on the past year about the wave. So the Bluetooth is a wireless technology with a frequency range 2.4 gigahertz to 2.48 gigahertz, used to send data between the fixed of the mobile devices over the short distance. Okay, based on information above, okay, Bluetooth is a type of what? Okay, so that's why you need to know. Okay, definitely it's not the infrared, it's not the UV lah. Okay, so it should be the microwave lah. Okay, so it's a kind of microwave. So just an example given here, question 15. It's not microwave lah. It's the ultrasonic. It's a high frequency wave for the high frequency sound wave. At least 20 kilohertz for the telecommunications. Let me see. 2.4 gigahertz. Gigahertz 10 power of 9 is here. Right? So it's in the range of the radio wave. In the range of the radio wave, so it haven't reached the microwave yet. Right? So microwave will be assist more than the gigahertz. Okay, so it's an ultrasonic wave. I think this one, the last year, I think there's some teacher asked about this. Okay, ultrasonic wave. Yeah, I think I need to study further about this one. Okay, for the Bluetooth. Okay, anyway, there's no much question in the applications of the wave. So just only 2 questions. How about the paper 2? Paper 2. Paper 2 is a second phenomena with ask you to differentiate between the transverse wave and the longitudinal wave, as I mentioned. Usually, we like the student make sure the student learns about the differentiate between the transverse and the longitudinal wave, as asking the last year. And then this is also the diffraction second phenomena. Right. So means that maybe this year they will ask the other phenomena will be interpolance. Okay. So I think that's all. There's no more wave questions here. All right. Okay, so for the chapter 6, chapter 6, we look at the formula. All right. So first, there will be focus on the diffractive index. So there are too many the different ways we calculate the diffractive index. So make sure you recognize all the symbol, especially the C here. This one is the speed of light. So there is a speed of light. Okay, which is a 3 times 10 power 8 meter per second, speed of light in vacuum. And this one is a critical anchor. Critical anchor, so they are different C. So, and we also have the near depth over the apparent depth. Okay, so here is the way how we determine the defective index. And we do have the defective index here by the Snell's law, right? So please be careful. There's a two different concept here. This one, it can be used in any two medium, right? When you apply the Snell's law. But if you want to apply this to determine anchor, I anchor R, here we have the sin theta 1, sin theta 2, right? Compared to this sin I, sin R, this I, we are specifically referring to the anchor in A or vacuum. It cannot be others medium, right? And then the R, let's say the R is a medium X, then you are looking for the defectiveness of the medium X. So that is the one you have to be alert when you apply this formula compared to the Snell's law formula. Okay, Snell's law formula, it can be applied between any two medium. Okay, so there's a big difference. And then this one is a length equations. So this length equation, we can use it to determine the characteristic of the image form, either by the lens or either by the mirror. So that day in school, I already discussed. So anyway, later I will go through again. So, and we do have the linear magnifications. So linear magnifications, we do apply on the thinner lens, which is the one that we study. For the linear magnification, I think that's all the formula involved. Okay, so first one, diffractions of light. So you're going to apply the way how we determine the diffraction index on the different example. Okay, so according to formula provided just now. So, and after that, when you apply the Snell's law, it can be any medium, right? Which just from here we understand that when the medium is optically denser, so you will have the bigger defective index. Bigger defective index, therefore you will have the smaller theta. So remember, because we have n1s, we have this n1 sin theta 1 equal to n2 sin theta 2. So it means when the n is bigger, you have to make the theta smaller. That's why from the example here, you see the medium 2, n2 is optically denser. Then we have the smaller angle. Same as wave phenomena that we studied before. When the light travel into the optically denser medium. So remember the 4S I mentioned. Okay. Okay, for the water wave also same. Okay, because we study on the same concept. Okay, we study on the same concept. So when we have the shallow water, okay, so smaller angle, shorter wavelength, slower speed. When apply on the light wave, when the light enter the optically denser medium, it becomes slower. When it's slower, you will have a shorter wavelength, you will have a smaller angle, you have the smaller speed. Only we don't have the shallow water lah, because the light, we're not talking about the water. The light, we're talking about the optical density. All right. So we apply 3S only lah. We apply 3S. So 3S and 1D, 3S 1D lah. So optically denser, so slower speed, okay, smaller angle, and then bigger N. All right. But in this case, we don't talking about the wavelength, right? Because we're more focused on the calculation part. We don't focus on the change in wavelength and so on. Right. Okay, so based on formula, we know that the product, this product here must equal to on the next right hand side product. So two quantity product equal to the other two quantity product, so the relationship will be inversely proportional. So that's why higher defective index will be have a smaller angle. Okay. So and there apparent depth. So I worry about the drawing. Okay. So I think the drawing you have to focus on see the different way on the drawing on the figure 6.11, 6.12. Okay, so which one is the image, which one is the object? It must be really clear. So like the 6.11, the image is the diver. All right. So the the image is the driver. So it means the driver become the objects lah. So the observer is the instructor. Observer is the instructor. So the from the objects enter into the eyes, so it will be bending away normal. But the instructor will see the image of the driver by the straight line. So that's why the driver appear vertically upwards. Okay. Same also when the instructor becomes the objects seen by the driver. So then the light will travel from the air into the water under the driver eye. So it will be bent towards normal. And then the driver will still see the instructor as a straight line because we never see the light is bending. We will just see the light is a straight line, but the light is bending under to our eye. So due to that, we will see that virtual image. And this image will be appear higher. Okay. So you see the difference here. Okay. And then this one will have the smaller apparent depth compared to the actual depth. Right. This one will have the bigger apparent height compared to the actual height. So because of calculation in the reverse way. Okay, calculation in the reverse way. So when we apply the Snell's law, okay, we apply the Snell's law. Okay, so in this case, the drawing is a difference. So you make sure that you learn how to draw. Okay. And what else? This is calculations parts. Just only alerts you when the calculation involved. When we substitute the formula, apparent depth and the actual depth, the depth is calculated from the surface down, from the water surface down, right? Not from the bottom up, right? From the surface down. So that's why we are looking for this hash and this hash. We are not using this one, right? We are not using this one. So that's why when the question gives you, okay, a mesh of the coin is seen at the height equal to the 2/7 of the depth of the solution. Okay, so you have to understand the meanings, especially when the ligand provided. When ligand is not provided, you have to make sure understand the meanings of the question itself. But usually the question in the SPM like this, it will provide the ligand to avoid the misunderstanding with the sentence itself. Okay, so you don't use a 2/7 here, but we apply on the others one. Okay, because the depth that involved, it should be calculated from the surface of the water down. Okay, and then the total internal diffractions. Okay, total internal diffraction, you have to understand how it occurs. First one, the total internal diffraction is only occurs when the light travels from the medium at higher optical density to lower optical density. Right? From the higher end to the lower end. From the higher diffractive index to a lower diffractive index. Right? Or the higher optical density to the lower optical density. This is mass. Okay, this is mass. Okay, and the angle of incidence is larger than the critical angle. Then only total internal diffractions occur. Okay, so the critical angle is what? Critical angle actually is an incident angle in the medium of a higher optical density when the angle of refraction at the lower optical density is equal to 90 degree. Right. So you can referring to this figure 6.19 to understand about this total internal diffraction. Okay, how is occurred? Okay, usually SPM like to ask about this total internal diffraction questions. They like it so much. I don't know why SPM. Even the last year they already have a question for it. Last year, where is it? I think there's a one special questions for this one total internal diffractions. Where is it? I think this one. All right. Okay. The sparkles. Yeah. This one's the total internal diffractions. It's asking about the critical angle with the different index providers. Okay, and then so how to make more sparking? More sparking means that you have you have to make sure that you're able to produce more total internal diffraction. Okay, so how to make sure there's more total internal diffraction? So the critical angle must be smaller so that you can easily occur total internal diffractions, right? Therefore, you can get more total internal diffractions of light. Then optical density must be the higher, because higher optical density you will have a smaller critical angle. Okay, so and then the surface must be the smooth. Okay, must be the flat. Okay, so that we can have more total internal diffractions. Because when the surface is not smooth or it's not flat, then the incident angle will be changing even from the same light of source. So when the incident angle changing, so it may cause a difference incident angle in the denser medium. Therefore, your total internal diffraction occur will be less. Then it will be unable to achieve the purpose of the question itself. Okay, so somehow please be more alert about this total internal diffractions concept. Okay, and all this is for you to study the applications, especially the optical fiber. Okay, it's very important in our daily life. Okay, and then the image formations of lenses. Image formation of lenses. All right, so I already show you how we draw. Okay, even the textbook is showing there's a 3 different line to draw. Okay, but I don't care. So you just need to learn, make sure that you learn how to draw at least by 2 different lines. All right, so let me conclude once for you. Okay, first one, you need the principal axis. And after that, you need the one vertical axis to present the positions of the lens, right? Present the positions of the lens. So let's say you have the convex lens. So this is a convex lens. Okay, so we draw the symbol of convex lens. So convex lens, we have the rear focus. When you have the rear focus, based on the phenomena, the light will penetrate through the lens. So the rear focus will be the light penetrate throughout the lens. So it will be the rear focus will be on this side. If the light travel from this way and penetrate through the lens, it will go through the rear focus. So this one is the rear focus. All right. Okay. If there is a virtual focus, when you have the convex lens, convex lens, you will have the virtual focus because the light penetrate to the lens. So, but we are focusing on the F before the light penetrate to the lens. So that's why this one we call it virtual focus. All right. So now if I combine it together, the way we draw is still the same. Okay, look at here. No matter where is your positions of the objects. So let's say here we have the 1F here as a reference. Okay, and then we have the 2F so that we know where is the object position. Okay, so if we have the object standing here compared to object standing here, compared to object standing here, or standing here. So as long as you have the objects, so the first line we're going to draw always the same. Make sure that you have a straight line from the object itself past the optical center here. Optical center here goes straight. So all will be the same. For object, past the optical center goes straight. Okay, no matter where is your positions of the objects, make sure the first line that you draw will be from the object pass to the optic center. Right, pass the optic center. So this is the first line they're going to draw. Second line, it will be the same from the object parallel with the principal axis. Second line parallel to principal axis. Then after that, it will be go through the focus. It will go through the focus. Okay, it will go through the focus like this. All right, and then after that, so that the cross-sectional point, it will be forming the image. So here you have the one image can be formed here. You have another image can be formed here. You have another image can be formed here, and then you have another image can be formed here. So only this one I will form. So you have to extend. You have to extend the line to the other side here. Extend the line to the other side. They only can form the image, right? So you have to draw the edge until they meet now. Then you can form the image. The problem is one of the image cannot be formed. Okay, one of the image cannot be formed because it's the two parallel ray. When the two parallel ray, right, so means that image is forming at infinity. When the image forming at infinity, we are unable to tell the other characteristic of the image. Even the textbook is mentioned here. This one, all right. Image form at infinity. At the same time, it did mentions in your textbook, it did mentions about the characteristics of the image. So it's possible do not mention lah, unless the question really asks lah, right? So what you should comment is only comment the image form in infinity. Because once the image form in infinity, we are unable to tell whether the image is a virtual or whether either the image is a real. Actually, we are unable to tell. So maybe you can say that okay, it sure will be magnified because when the form infinity will sure it will be bigger, 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 and bigger. The problem is we cannot comment whether it's upright or inverted. Either it's a virtual or real because infinity on the positive side, infinity on the negative side. So we don't know where is it. All right. So for me, we only can comment image at infinity. All right. Okay. So the rest you can try to differ compared to the like game that I told you how to draw. Okay, all put it together. Okay, when it comes to the concave lens, so concave lens, we're referring to the virtual focus, which is this one. We're referring to this virtual focus. So Sam, one of the line that you need to draw, let's say we take any ones here. So first one, you must form this line, this top of the object toward the optic center. So go straight line. And then second, still the same, parallel to the principal axis. Just now we go to focus, right? So now we will go to focus also. Focus is here, virtual focus, but we extend it to the other side. Because the light have to penetrate. The light have to penetrate to the lens, right? So it means that the image forming here will be the virtual image. So virtual always stand upright. Virtual always stand upright, right? Virtual image always upright. Real image always inverted. So this pairing you must know lah. Okay, and when we apply the lens equations, 1 over f equal to 1 over u plus 1 over v, right? So f is a focus length, u is object distance, v is the image distance, right? Okay, so to apply this lens equation, get to know about the characteristic of the image. So you have to first you have to very clear when you have the convex lens, it's a real f, real focus means it's a positive f. Compared to the concave lens, so it's a virtual focus, so it means it's a negative f. So when substitute formula, you have to remember which one positive, which one's a negative. And then afterwards, you can put any numbers, okay, for the f and the u. Let's say the question say, see whether we have questions or not. Paper one last. You see this one. These questions are this like game. I think this is repeat 3rd or 4th times already in the past 20 years SPM, right? So I don't know why they can't change others like game. Okay, this one's a mirror. Even the mirror, we also can apply the calculations to know about characteristics of the image, right? So let me repeat again here. Okay, 1 over f equal to 1 over u plus 1 over v. So when we apply calculation, first thing you must know when you have the lens convex. Okay, convex lens. Okay, convex lens means that the f is positive. So when you have the concave lens, so the f is negative. So at the same time, convex lens, understanding the calculation also can be applied on the concave mirror. So vice versa for the concave lens, it also can be applied on the convex mirror. So since we have the concave mirror here, this one concave mirror. So concave mirror, we apply the same concept as a convex lens. So the F is a positive. F is a positive, so we have to apply F positive here. Okay, so now based on this question, so this one I erase it. So it's good because everything is given already. Even it's not given, it's fine. We can put any number that we like, the lucky number. So as long as we know that this object located bigger than F. And only the difference is what? This one given a special values already. So it means that we have the U. We have the U equal to 10. This is a U. Then this is a F, 5. So it's positive 5 because the F should be positive. Then we substitute here 1 over 5 equal to 1 over 10 plus 1 over V. So 1 over V will equal to 1 over 5 minus 1 over 10. So 1 over V will equal to the 2 minus 1 over 10. So equal to 1 over 10. So it means that the V is equal to 10. Right? So V is equal to 10. So now we already know V is positive. Remember, when you get the answer V positive, means that it's a real image. When it's positive, it's a real, image will be real. When it's negative, means the image will be virtual. So when there is a real image, real must pairing with the inverted image. Real always inverted, virtual always upright. So real inverted is a pairing. Okay, and then about the size, so V is a 10, U is 5, U is 5. Sorry, V is 10. U is 10 also. So sorry, U is here. Okay, sorry, yeah. U is 10. So V10, U also 10. Means they are same size. Because at here we can apply another formula provided. Remember, there's another formula provided here, linear magnifications. So M equal to the V over U. So when the V 10, U also 10. So at the end, magnification is 1. Magnification 1 means that they are same size. Okay. So here, real, same size inverters. Answer A. So diminish is wrong. Okay, same size correct. Okay, upright is wrong. Virtual is wrong. Okay, so diminish is wrong. Virtual is wrong. Upright is wrong. So that's why answer is A. So even we no need to draw. Okay, we can get the answers by calculations. We don't need to memorize. Just apply formula calculations. Okay, so you no need to memorize all these things. Don't need to memorize which image position, characteristic of the image on the different object position. If you do so, sure you cannot score. Even it come to this one, you see, for the spherical mirror here, we have another one's tables. This is the one. The question asking just now is object at C, which is U equal to the 2F. F is 5, U equal to 10, so U equal to 2F. You see the real inverter, same size. Okay, so no need to memorize. Please do not wasting your time go and memorize all these things. Apply the calculation, easier for you, or apply the drawing method, even better. Because drawing method, you're able to know the characteristic of the image. At the same time, question may ask you to draw. Okay, in the paper 2. So that's why it's very important get to know how to draw the ray diagram to form the image. Okay, so no matter whether you learn draw or you learn calculation, but for one thing sure, please do not memorize. Don't wasting your life. Okay, I know there are many teachers ask the student memorize, but not me. All right, if your tuition teacher asks you to memorize, by right you should ask to pay to refund back the money that you pay, wasting time. Okay, so this one, okay, about the applications of the lens. Okay, so again, 10.2 show the ray diagram, convex lens with the same focus length in the camera, which produce an image of the H1 and H2. All right. So now this one, as you can see, with the same focus, only the different object distance. All right. So U1, U2. So U1 is more than U2. U1 is more than U2, and we get to know the H1 is less than H2. Right? So just based on the comparison, you see, all right? So when the object distance increase, U1 bigger, the hash image will be smaller. So, okay, no increase, no same. So when object distance decrease, so the image increase. So answer D, 17, non-key. All right, so 17 non-key. Okay. So based on observation, this one, the question just like the paper 2 question 5 or question 6, or maybe the essay questions 11. So it's the same thing, right? Observations and give the conclusions. And this one also same. Basically, the question 17 and 18 is just like the same, okay? Because on the different object distance, the view from the camera, different object distance, okay? Okay, and this graph, okay, image distance V against the linear magnification. So based on the formula, since they're asking about the linear magnifications and the image distance, so we have the magnifications, go to the formula this here, M equal to V over U, right? M equal to V over U. So now you have the V against M, so it means that the V will equal to the MU, or we change it into the form of the V equal to the UM, which is compared to the equation Y equal to the MX, right? So this one's a X, this one's a Y. So then we have this one intercept here. Intercept here is X. So we got intercept here is X, then how? Okay, so and here, what is the U? X is what? Okay, so in this case, how are we going to make the change here? We need to, because from here you can see that it shouldn't have the what? It shouldn't have the intercept, because it should be the V equal to the UM, right? Which is the gradients themselves showing the object distance. But since now we have the intercept, so it doesn't obey this Y equal mx plus c. So what is the c? C is missing. Then we have to find. So only thing that we can do is try to change this u. So we know that 1 over f equal to 1 over u plus 1 over v. Okay. So the f in cell is what? F in cell is uv over u plus v. Okay. So you have to find the way how to substitute it into the formula. Okay, so definitely you need to do some calculations based on the suggestion here, right? You see, it's apply the same thing. All right, so you have to do some substitutions on the formula. They're only able to know, okay, what is the meanings of the f here. I think this question I given in the trial before, so we already discussed before. Okay, so when you have a problem like this, you have to find a way how we change the formula. When you refer back to the formula list, the only possibility that you want to delete this formula is only with the distance equations. All right, so that's why you need to do some calculations until you get the format similar as a y equal to mx general equation. Then only you need to be able to know the intercept is presented what. So here is an example show here. All right, you can try the other way as I show you here. You can try to do like this. Okay, if you think it's difficult, then you try to rearrange it so that you can get to know, okay, from here u equal to what, then you can substitute it into the formula. Okay, so or you from the beginning here, you see this one m equal to the v over u, actually equal to the v multiply 1 over u. So 1 over u is what? Okay, from here 1 over u is equal to the 1 over f minus 1 over v. So substitute here v equal to 1 over f minus 1 over v equal to the magnifications. Then rearrange the equations so you will know the formula in the formats of the y equal to mx. So you must try. Do not just only study. If you study later on when you do, you can't recall back the solution step, then you will die. So that's why you must try to do on the different alternative way. Okay. So what else they need to know here? Okay. So regarding the applications, so this question I already touched. Okay. So next one is optical instruments. Optical instruments, your main focus will be on the telescope and microscope, compound microscope and the telescope. Right? Where is it? Compound microscope and wait. Eh? Scroll down too fast. Okay, and the formation of telescope here. Right, telescope. Okay, here, telescope. Telescope and microscope. Okay. So if you study this and you study this, I got no confidence you really can understand that. Right. So today I already told you, I made the conclusions for you already how what you should be focused. All right. So when you're going to know about this normal adjustment, okay, knowing about the length between the lenses. Okay. So today I think in the class I already discussed before. All right. So for the Simon and Charles, am I discussed before? I've forgotten, sorry. For Francis, I already discussed already. So anyway, there is the class I conducted for the Form 4 students before this. If you follow, then you can recall back it. So I think the video I haven't uploaded to YouTube. So later I find the video, I will upload to YouTube. I will share with you regarding the detail. How can easily understand the difference design or the structures on the telescope and the microscope. So later I will share the video. So give me some time. So sure I will share it to you by today or tomorrow. Okay, so that you can go through again regarding this telescope microscope. All right. So I think that's all for this one. The mirrors one, just now I already touched. So regarding how we determine the characteristics of the image, only the drawing I didn't touch yet. So still the same. The drawing basically is similar to the mirror. You need the principal axis and you need the vertical axis to present where is the positions of the mirror. Okay, so when you have the concave mirror, look at the curvature. So the F will be this side if you follow curvature. And if you have the convex mirror, the F on the other side. Okay. So in this one, here is a negative. This one is a positive. Positive is the real focus. Concave, we have the real focus. And then the convex mirror, we have the virtual focus. Because of what? Because now the light phenomena here is different. This one is the deflection. Just now is the second phenomena, diffraction. Right. So the light will penetrate through the lens and come out. But this one, the light will hit the mirror and deflect. Hit the mirror and then deflect. So the real light, it will be in front the mirror. So that's why after the mirror will be the virtual. It's not like the lens. After the lens is the real. Before the lens is virtual because of the light phenomena itself. All right. Okay. So when the convex mirror, because of the curvature, our F is on the virtual F. So that's why we're referring to this F when we draw. Okay, when we draw to get the diffracted light. Okay. And then for the concave mirror, because it's a virtual F, it's a real F, follow the curvature. We follow curvature. This one, the curvature is here, means a circle. So the F are inside the circle, right? And then for the convex mirror, we follow the curvature, so the F are inside the circle. So this is how we know where is the positions of the F. Okay. And for when the light deflect, so it will deflect by the concave mirror will be deflect to the real focus. All right. Okay. And drawing still stick to the same concept. Only the slightly different is mirror, we don't have the optic center, but we have a center of the curvature. So when you have the concave mirror, so the F is here, then we have another one, is a center of curvature. So which is located at the 2F. All right, center of curvature. And for the concave, okay, convex mirror, we have the F, virtual F, which is a negative F, right? Convex mirror. So, and the center of the curvature will be here. It's a negative 2F here, okay? So remember, this one is a convex mirror. So same as our understanding for the concave lens. That's why the F is negative. F is negative, all right? So we have the 2F here. Okay, so when we have the objects, no matter where is your objects, so when you have the objects here, when you have the objects here, when object here, when object here, objects here, so same, right? From the object, we try to draw one straight line to the center of curvature, go straight. Right, unless you stand above the C, that cannot draw. So if not, then this one go straight to the C and then we draw to the other side until hit the mirror, something like this. Okay, until hit the mirror here. So you have to extend this line, You have to extend this line. Okay, so and after that, okay, another ones. One object to the center of curvature, go straight. Okay, one object to the center of curvature, go straight. This is the first line you must draw. Just like the lens, the first line you must draw from the object to the optic center. Okay, for the mirror, from the curved mirror, okay, from object toward the center of curvature, straight line. So this is the first line. Second line is the same from the object parallel with the principal axis. From the object with parallel with principal axis, then afterwards to the focus. Then you see where they meet. Right? After that, you will get where they meet. So if I focus on the one drawing, it may be easier for you to learn. Example like this one. So first line, we're going to draw from the object to the optic center of curvature. Center of curvature, go straight line. Okay, then afterwards, second line, parallel with the principal axis until the vertical line here, and then afterwards deflected to the focus. Then you get the image already. Then you will get the image. So here you are, the image is forming here. So this one will be the rear inverted. Okay, okay, keep talking 2 hours, no sound already. All right, okay, so you will have you have the rear inverted and the diminished. This is how we draw. So if you don't want to learn this one, so maybe we can learn the other ones. So let's say our object standing here. So same. First line, we're going to draw from the object to the center of curvature. Go straight. Second line, from the object, parallel with the principal axis, and afterward to the focus. So as you can see, if a split apart cannot meet, so it will meet on the other side. So we extend it. It will meet on the other side, and extend also for this line until they meet. So they meet on the virtual side. So that's why the image form will be here. So this is the image here, and then this image will be the virtual image. So virtual upright. Virtual is always upright. Okay. So make sure remember after complete your again includes the direction of the light ray. So for this one, okay, the directions of the light ray, okay, from the center of curvature go to the middle and deflected back. And for the other ones, okay, parallel toward the principal axis to the mirror and deflected to the focus. All right, so it will deflect. Then image forming on the other side, so it's a virtual image. This is drawing. So the calculations one to get to know characteristic of image, I already showed you just now. So I think that's all for this chapter. So remember that I will share you the video for this detailed discussion about the telescope and microscope. Hope that you got time to go through. I think that's all. All right. So after this, if you have any questions you want to ask for these two chapters, you can ask anytime in the group. All right. So that's all. See you later afternoons for the other slot for the Form 5 chapter 1 and Form 5 chapter 2. Okay. See you later. Thank you. Bye bye.